in pipes, but the fluid will be considered as incompressible. What it means? That now we will treat density as constant, but we can have a topic, unsteady flow of compressible fluid in pipes. Then in that case, you have to treat the density as variable. So it is from problem to problem that which flow types and regimes we consider in the analysis. So we consider an element of pipe flow. Before we discuss and derive the equation, we already studied steady flow of incompressible fluid in pipes. We already studied in chapter 8. Now we study unsteady flow of incompressible fluid in pipes. So we consider a fluid element here, a cylindrical fluid element, and now the same forces that were acting there in the first topic of chapter 8, where we developed the Darcy-Weisbach equation, we will proceed along the similar lines, but there we treated the fluid flow as steady. Now we will consider it as unsteady flow. So we have these two forces which are acting, F1 on this element here. The cross-sectional area is A, radius is R. This is pipe flow. So we consider cylindrical fluid element. Now F2 is P plus dP into A, differential change in pressure multiplied by this A. The vertical distance between the two ends of the element, that is denoted by dz. The horizontal distance, that is not horizontal, but in this case, since it makes an angle theta, this dimension is denoted by ds. The fluid is flowing with a velocity v, and because the fluid is flowing in pipes, shear stresses will develop, and these are denoted by tau naught, as we did in chapter 8 also, the wall shear stress, tau naught. And this is the weight of the fluid, because you can see this fluid has a weight, and this is vertically down since the axis of the element is inclined, so that's why it makes an angle of theta with respect to the axis of the pipe. So now that we can understand these various parameters, we can proceed to develop equation for unsteady flow of incompressible fluids in pipes. So consider an elemental length of flow in pipe. We will apply the Newton's second law. So this we did also in chapter 8, first topic, when we tried to develop the Darcy-Weisbach formula. But in that case, you remember we put this MA equal to 0 and we solve for the forces. Now we have unsteady flow, so now it will not be equal to 0. And we are going to now develop the equation. So for unsteady flow, now since acceleration is not equal to 0, so the acceleration can be expressed as A is equal to V dV by ds plus dV by dt. So this equation, if you have studied Franzini, chapter 4, basics of fluid flows, in that you might have come across this equation. You study it. It is written there, chapter 4. So what is this equation? The acceleration that we can write down for unsteady flow. What this equation says, V into dV by ds. This first term, this is known as convective acceleration. This is known as convective acceleration. And this convective acceleration, it will become 0 when we have uniform flow, because in uniform flow, velocity is not changing with respect to distance. This is what you learn in fluid 1, that when the velocity is same at all points in the flow, the velocity is same at all points in the flow, then the flow is uniform flow. So in uniform flow, then this term will be 0. This second term, this is known as local acceleration. This is known as local acceleration. dv by dt, velocity is changing with respect to time. If we have a steady flow, then in that case this can happen. Clear that this dv by dt will be 0. Okay. Now the thing is that this is the acceleration for unsteady flow. Now we can take summation of forces in along the axis of the pipe. So we apply the Newton's second law. Summation of forces F is equal to ma to the cylindrical fluid element. Clear? So now in this case F is equal to ma. Now a is given by this equation here. So we have this F1. Let us assume that in this direction the force is positive. Let's say this direction force is positive here. So we have F1 minus F2. This is F1 in this direction minus F2 in opposite direction minus dW into cos of theta. Because this is dW, now we need its component along the axis of pipe. So you can complete a triangle here. If this is 90 degree, if this is 90 degree, so then in that case what is happening is that dW cos of theta that we have to consider, and we have shear stress all around this. So it will be shear stress multiplied by this surface area over which the shear stress acts, and this must be equal to ma. Now ma is not 0, because if you remember in the chapter number 8 when we discuss the Darcy-Weisbach formula, we equate this to 0. We equate this to 0. But now in this case, the flow is unsteady. So when the flow is unsteady, now you can see that in this case, what is the situation that we have ma. This is equal to ma. Clear? Acceleration is not equal to 0. Unsteady flow. If a steady flow, we will say this is equal to 0. This is what we did in Darcy-Weisbach formula derivation. You go back. So now we bring unsteadiness and the fluid is incompressible. So now the problem solution nature has changed, and now we have equal to ma. Now we put the values for these forces. So F1 is equal to PA, F2 is P plus dP into A, and this dW, this is the weight. So you already studied that specific weight is equal to weight by volume. Now from here, this gamma, this can be written as rho into G. So W can be written as rho into G into volume. So what is the volume? A into ds. Area, cross-sectional area is A multiplied by ds is the volume. So that's why this can be written as, this is rho G into volume. This is what we have written here. And then cos of theta. So cos of theta you can calculate for this element, dz by ds. This is dz and this is ds. You can calculate. Next we have tau naught into ds. So tau naught is here. And what is as? 2 pi r, because this is acting over the circumference. So 2 pi r into ds. 2 pi r into ds. This is the area over which the shear stress is acting. So area multiplied by shear stress, we get the shear force. And mass. So mass is equal to rho into ads. Because we studied that density is equal to mass by volume. So now volume is ASDS. So rho into ASDS, that is equal to, this is your M. And acceleration is this term here. This is your acceleration from here. Because now we are treating flow as unsteady. So now you see unsteady analysis. Now we try to simplify this equation. So dividing by gamma and area, you put pi r square and simplify the above equation, we will get this equation. You just simplify this equation here, this equation, you simplify this equation, you will get this equation. Now we note that VdV, which is written here, this VdV can be written as half into dV square. How? Because we already know that, let's say this half into d into v square, if I take the derivative of this, so what will be the derivative? It will be equal to 2v divided by this 2v into dv. So now 2 cancel, and we can write down this is equal to v into dv. So that's why v dv I can replace with this quantity here. So now this equation then becomes this equation here. So let's say this is equation number 1. This equation is now applicable for unsteady flow. Why we have unsteady flow? Velocity is changing with respect to time. So this equation is for unsteady flow. And it is applicable to both compressible and incompressible fluid. Why? Because gamma is present. If gamma is variable, it is for compressible flow, steady and compressible flow. If we treat gamma as constant, then it will be equation for unsteady flow and incompressible fluids. This is what we are going to study in this topic. Unsteady flow of incompressible fluids. Because compressible fluids, we are not very much interested, as I said before. Maybe chemical engineering, mechanical engineering, they study steam turbines, thermodynamics. So they may be interested in compressible fluids. Mostly civil engineers, they are dealing with water. Water is treated as incompressible for practical purposes. So this is how we look to the question. Not only from steady or unsteady point of view, we think and then we say why we say about compressible and incompressible. So we just see the problem is occurring in which domain, and then we bring all those concepts in the solution of the question. I hope now you understand very well. Now let us further simplify this case, because we have to develop an equation for unsteady flow of incompressible fluids. So now essentially we will consider this gamma as constant. And still it is unsteady flow because this term is present. Velocity is changing with respect to time. So now for incompressible fluid, we consider gamma as constant and we can integrate this equation. So when you integrate this equation for some section 2 and 1 points which are L distance apart, then we get this equation. Clear? P1 by gamma minus P2 by gamma, Z1, Z2, V1 square by 2G minus V2 square by 2G. This is for section 1 and 2. Because we integrated that equation for 2 section, the distance between the two is L. That's why ds is now replaced by dl. ds, because now the length we consider is L, so ds is now replaced with L. So this is now the equation. And in here, gamma we consider as constant. So now we know that hydraulic radius is equal to d by 4. D is 2 times, radius is 2 times the diameter, so r by 2. And now we can put this r by 2 here as the hydraulic radius. So we get this equation. And if you remember the Darcy-Weisbach formula, if I ignore this term here, if I ignore this term, this is what we get when we try to derive the Darcy-Weisbach formula. This is what we get. And then we find out that this term is essentially equal to your HF. And this is how we bring in the major head loss. and so on. But now we bring the unsteadiness into the problem. So that's why this additional term comes due to the unsteadiness in the problem. So when there is no acceleration, what will happen? Then the flow is steady. V is constant. So dV by dt will be 0 because velocity is not changing with respect to time, and V square terms drop out. Clear? So then in this case, we are left with this equation. P by gamma plus Z minus this equal to P by gamma plus Z at second point. So essentially here what we are saying that V1 square by 2g is equal to V2 square by 2g. So then what we are essentially saying, we are saying that let's say the flow is uniform because velocity is not changing with respect to distance from one point to another point. So now in this case, what we have? We have steady flow. This is now steady flow. What about the fluid? Fluid is incompressible. What about the uniform, non-uniform flow? Flow is uniform. This is how we bring in all these concepts when we solve fluid mechanics problems. So now let us come back, and if we consider this equation number 2, so what we do is that this equation, if you compare with the equation that we developed for steady flow of incompressible fluid in chapter 8, what we find out that this HF is essentially equal to this tau naught L by RH into gamma. This is what we get. You go back and revisit that derivation, you will see this term there. So that's why this is what? This is the pi friction head loss over the length L. And then we said that because it is very difficult to measure this shear stress, so what we did the dimension analysis, and we calculate the value for this tau naught, and then we put here, and then this resulted into the Darcy-Weisbach equation that HF is equal to F, the friction factor, into L by D into V square divided by 2G. This is then what essentially in the end we get. This is what we get last time. Steady flow. Now the flow is unsteady, so that acceleration terms come into the analysis. So that's why this we can write down as HF. So that's why we can write down the three forms of energy at section 1 minus HF is equal to this. Ignore this term. If I ignore this term, what is this equation? Steady flow. This is what we developed in chapter 8, treating as steady flow. The chapter name was Steady Incompressible Flow in Pressure Conduits. Now we are studying unsteady flow, so this unsteadiness comes by this term. So now we can write down that this is your H, the total head, minus the loss due to the friction, and minus this term, which is the accelerative terms, because we have unsteady flow. This is equal to the total energy at the second point. So now this equation, this is acceleration head. If we denote this by H as the accelerative head, now this 4 equation states that the energy loss between 1 and 2 is equal to that required to overcome the friction, this one, and that required to produce the acceleration in the fluid flow. So it means that now the energy loss in the pipe flow, what was considering only the major head loss, the minor head loss, we solved the problems. And now your question is that if we consider unsteady flow, then you have to bring in this in your analysis to solve the problem. You can see here that we have steady and unsteady flow of incompressible fluid in a horizontal pipe. Flow is the same for all the three cases. Now in this case we have the steady flow, so MA is equal to 0. This is what we did in chapter 8, and we get this HF is equal to this value. So you see that there is a drop in the energy. Since the pipe is uniform, velocity we do not consider, that is the same at both the sections. So P1 by gamma, and then it reduces to P2 by gamma. Z1, Z2 also same. That's why only difference of pressure equal to this. We have the head loss due to the friction. Now the same problem, if you consider the flow to be unsteady, then you can see here that, you see, because if you bring unsteadiness in the same problem, not equal to 0 now, and P2 will be less than P2. This P2 here, which is shown here, P2 dash here, it will be less than P2. Why? Because we already stated that there will be more loss of energy due to this accelerative head because of the unsteadiness. So that's why you can see here that we have the head loss due to the friction, same in all the cases. Due to the friction, the head loss is the same. HF value is the same. But because of acceleration, there will be further loss of energy given by this term. So the pressure head will be further depressed. When we have acceleration in the flow, the fluid flow is accelerating. And then this is the equation. Because it is accelerating, that's why dV by dt is positive. And if it happens that there is deceleration of flow, then in that case, this term will go up, Lg by dV by dt, because dV by dt is now negative in this sum. The fluid is decelerating. Acceleration is in opposite direction to the velocity. So that's why this P2 double dash, it will be greater than P2 in this case. So that's why this term will bring the pressure up by this amount here. This is how we look to the problem from different angles. Now the next thing is approach to steady flow. In this topic, what essentially we are looking for, that when we have a water in a tank, so you can see at this point 2, the water that is going to flow out, it will be under this H head, as we already discussed. So when you suddenly open the valve, the water will rush out from this here at this point. So of course it is unsteady flow problem. So in this case, what is happening, that the flow will accelerate because the flow occurs under H. So what essentially will occur in here, what will happen? What will happen? You want to calculate. This is happening, look here, that when the flow occurs at this point 2, when you suddenly open the valve, so the flow will accelerate. But as the time passes, this flow, it will try to approach to steady flow. Now we are not saying the flow will become steady flow. That's why the topic is approach to steady flow. So this time we are interested to calculate that when you open the valve, the flow will accelerate due to this head available, but then as the time passes, it will approach to the steady flow condition. Approach, remember. So when it approach to that steady flow condition, how much time it will take? This we are interested to calculate now. So determining the time for the flow to become steady in a pipeline, when a valve, here we consider a valve, when a valve is suddenly opened at the end of the pipe, can be accomplished through this application of this equation. We can apply this equation to calculate that time in which the flow will approach to steadiness. You see here this dt is present. We can calculate this time here. that in how much time the flow will approach to steady flow condition. How much time it will take for flow to be 50% of the steady flow condition, 70% of the steady flow condition, 80% of the steady flow condition. This we are interested to calculate in this topic, approach to steady flow. So immediately when we open the valve, the head is available, this H is available to accelerate the flow. The flow will accelerate because suddenly you open the valve. Thus flow starts. But as the velocity increases, the accelerating head is reduced by fluid friction and minor losses. The flow will accelerate when you open this valve, but that will decrease with time. Why? Because we have friction losses occur. Earlier we stated that this energy, which is loss, as the fluid moves from one point to another point, the energy loss is occurring in two fashions. So that's why what I said, that as we open the valve, flow will start, but as the velocity increases, the accelerative head is reduced by the fluid friction and minor losses. Because in the Darcy-Weisbach formula, it is proportional to V square. Clear? So that's why now we are interested in this topic to calculate the time. How much time it will take that this unsteady flow, or let's say unsteady flow velocity, it will approach to the steady flow velocity, which is the flow velocity under steady conditions. So now we talk that because the frictional effects and the minor losses have effect on that. So the total head loss, this is now given by this equation here. Now remember, this is all the losses. This doesn't mean that this is only the minor losses. No. You see, we have H. Whenever the term HL is written in your textbook, it is all the losses, major plus minor. We studied that HL is equal to HF, the head loss due to the friction, and plus H dash. So that's why it is all. You see, we write down HF. How we write down HF? This will be equal to F L by D into V square by 2G. So this can be written as K. So we have H is equal to KV square. So that's why this is not only just minor loss, that you remember that, because only minor loss is expressed as velocity head with a loss coefficient. So this is the total head loss, where KL is a constant and it may vary with velocity unless the pipe is very rough. So this KL is now equal to FL by D plus summation of K. This summation of K is now the sum of the coefficients of all minor losses in the pipeline that we studied in chapter 8. Consider everything that comes in the problem. So now for section 1 and 2, we already write down this equation because we stated the time can be calculated from this equation 4. So just this equation now we write down for two sections. For section 1 here and for section 2 here. So we write down that equation. That equation HF. This equation here HF. Only friction losses, but now we consider minor losses also, so it has become HL. That's why this is written here as HL, not HF, because now we consider the total head loss, and this is the accelerative head, because we have unsteady flow condition. If flow is steady, this will be 0, and this is what you did to solve the problems. You essentially treat the flow as steady flow. Now we bring the unsteadiness. So we bring this additional in the analysis to solve this type of problems. This is how we find solution to the different flow situations. Okay. So now we know that at point 1, pressure, and at point 2, when the flow come out, again atmospheric pressure, and the velocity V1, very, very small as compared to velocity in the pipe flow, that is 0. Similarly, Z1 minus Z2, if we treat this as the datum, if this is our datum, then you can see that Z1 minus Z2, that is essentially H, which is written here. So we can simplify this equation as here. Now we can write down this as here. We just rearrange this equation, bring this V2 square by 2G on the other side. So now we can write down only just V. So this is now H, and this can be written as KV square by 2G because this is K, capital K and small k, clear? This can be combined with this and we just bring this term here. And now this capital K, this is equal to FL by D plus summation K plus 1 here. This is 1 here. So just remember that for free discharge 8.2, the expression K will be equal to KL plus 1. The 1 represents the residual velocity head. Now K, summation of K does not include the submerged discharge loss coefficient. You remember KD equal to 1. We studied about the submerged discharge loss. So because in here, it will represent the residual velocity head. So that's why summation of K should not include the KD is equal to 1 term. If, however, this is for free discharge. This is for free discharge. If we have a submerged discharge, then K will be equal to KL, and now this K, it will include the KD equal to 1. So it means that when we have free discharge or we have submerged discharge, essentially it is same. Either K1 is here or this K1 is here. Essentially same. So that's why there is no problem that at point 2 we have free discharge or we have submerged discharge. We get the same applies. If, however, we neglect the minor losses, then this is a residual head. This is not a minor loss then you have to consider this. So the situation will be different if we ignore the minor losses in a problem. So because now we want to approach to the steady flow, so let's say the steady flow velocity is Vs, and because we are now moving towards the steady flow situation, then we have to essentially treat dV by dt equal to 0. So then in that case, this equation simplifies to this equation. V becomes Vs and this term is 0 because dV by dt is 0. So for steady state velocity, this is the equation that you can use to calculate. This Vs will calculate for you the steady state velocity. The flow will be steady flow. So now from this equation, we can put the value of H, and that we can bring it here in this equation 1. Take the value of this H, we want to eliminate H and bring it here because this Vs we want to bring here. So this is what we do. Put H from equation 2 in equation 1. So now dt is equal to this. You have the unsteady flow velocity V and approach to steady flow. Velocity at steady flow. That now we bring in this equation number 3. And now we can integrate this equation. And we can calculate that how much time it will take for flow to approach to steady flow condition. We are not saying that the flow will be 100% steady flow. No. Approach to steady flow. How much time it will take for V to become 50% of Vs, 70% of Vs, 90% of Vs. How much time it will take for V to approach to the steady state velocity, how much time it will take. This is what we are looking for under this topic. So now if we treat F and K as constant, we can integrate equation 3, and noting that constant of integration is 0 because when V is 0, T is 0, and log of Vs by Vs is 0. If you just learn to evaluate this integral, you will get this equation. So this equation you can use to calculate the time when V approaches Vs. And this is applicable to submerged discharge as well as free discharge. We already discussed. And this equation indicates that as V approaches Vs asymptotically, and that the equilibrium will be attained only after infinite time. This equation is telling us that this V will approach Vs. It will require infinite time. Why? Because when this V is equal to Vs, anything divided by 0, it will make the time infinite time. But practically we see that it will approach to the steady condition because we use simplifications, consider other factors. So in reality, there will be elastic waves and damping. These factors will be responsible so that true equilibrium will be reached in finite time.